Let's get at her. Chemistry 3101. We're now on the last section of Chapter 2, which deals with the resonance hybrid and delocalized and localized lone pairs. So the very last section of the chapter. Anyhow, I told you that you need to be able to draw resonance structures. However, I don't ask my students to draw the resonance hybrid. If there's one thing I need you to understand about resonance structures, it's that the molecule is not vibrating back and forth from one resonance structure to another. This is not happening. What resonance structures represent is how electrons and charges are delocalized throughout the resonance structure, and it's difficult to draw one structure that shows you all the delocalization, and so we draw several resonance contributors, and all of those contribute to the overall resonance hybrid. You can draw a resonance hybrid, but chemists find it oftentimes most useful to draw individual resonance structures. So the resonance hybrid represents, it's not working, here we go. The resonance hybrid represents the pi bond of an allylic carbocation as being delocalized over 3 carbon atoms. That's what's shown here. This dashed line represents the pi bonds, okay? The partial positive charges represent how the positive charge is split between the 2 carbon atoms on the end. And the thing is that the resonance hybrid is consistent with molecular orbital theory, and that both of the pi electrons occupy a bonding molecular orbital. It has no nodes. It has no nodes, and so the electrons are spread out across all 3 carbon atoms. Let's talk about delocalized lone pairs. When we talk about localized electrons, these are electrons that are not involved in resonance. And when we talked about delocalized electrons, these are ones that are involved in resonance. In order for a pair of electrons to be delocalized, the pair has to be adjacent to an atom that has an unhybridized p orbital. Why can we draw these curved arrows that we drew already earlier today for an amide? We can draw these 2 resonance arrows, which would produce this resonance structure. I kind of didn't give myself a lot of room here, but I would end up with this. Well, the reason why we're able to do that is because this lone pair right here is adjacent to an atom that has an unhybridized p orbital. Where is that unhybridized p orbital? It's on the oxygen atom. Remember that when oxygen has a sigma bond and a pi bond and 2 lone pairs, it is sp2 hybridized. And so since this oxygen is sp2 hybridized, that means it has an unhybridized p orbital. This carbon is also sp2 hybridized, so it also has an unhybridized p orbital, like that. So here's our atom that is adjacent to the lone pair that has an unhybridized p orbital, and that's why we're able to draw this resonance structure. In one structure of the amide, the nitrogen is sp3 hybridized, and in the other one, it's sp2 hybridized. And so you might be wondering, well, which one is it? Is that nitrogen sp3 hybridized, or is it sp2 hybridized? This is something that I think is wise for you to memorize. And the reason why is because it comes up from time to time, but so infrequently that students tend to forget. And so I always tell my students, it's a good idea to memorize this. Since the lone pair is delocalized, the only way that it could be delocalized is if the nitrogen is sp2 hybridized. because then you'd have 1, 2, 3 overlapping unhybridized p orbitals, which would form a conduit for the electrons to move through. A lone pair does not participate in resonance if it cannot overlap with an adjacent p orbital. Then it's going to be a localized lone pair. If you take a look at the lone pair on this nitrogen in this compound, and this compound is called pyridine, okay? We have the nitrogen that has a lone pair on it, but it also has a pi bond on it. And you might be saying, well, if I've got an allylic lone pair here, why couldn't I draw these two curved arrows and draw this? Well, this is in fact not a valid resonance structure. This is the second thing from this chapter that I highly recommend that my students memorize. The lone pair on the nitrogen in pyridine is sp2 hybridized. sp2 hybridized. This is sp2 hybridized. Why would that be? Well, the reason why is because if you look at that nitrogen atom, which is shown right here, that nitrogen atom already has a pi bond attached to it. In order for it to have a pi bond, how do we make a pi bond? A pi bond is formed from the side-to-side overlap of two p orbitals. That means there's already a p orbital on the nitrogen. It is shown right here. So if we already have a p orbital to form the pi bond, that means that the lone pair cannot be in a p orbital. And so since the nitrogen has 3 regions of electron density, it's sp2 hybridized, and thus the lone pair must be in an sp2 hybridized orbital. This is the second thing that I think my students should memorize from from this section. So I'll put here memorize. So to repeat or to recap, I would memorize that the lone pair on the nitrogen of an amide is sp2 hybridized, or sorry, that the nitrogen of the amide is sp2 hybridized. And I would also memorize that the lone pair on the nitrogen of pyridine is sp2 hybridized. Just because a lone pair is delocalized, don't assume that a lone pair is delocalized just because it's next door to a pi bond. If we look at this lone pair here on the nitrogen, it is next door to a pi bond, and we have an allylic lone pair, but it is not resonance stabilized. It does not participate in resonance. We can't always assume that. However, there is a general rule that you can assume that when an atom possesses a pi bond and a lone pair, there's no way that they can both participate in resonance. And as always, if there's no p orbital next door to the lone pair, then it's going to be localized. And so if we look at this molecule right here, we have 3 lone pairs. Let's draw them all in. You can see one of them's already done. So we have a lone pair here, we have a lone pair here, and we have a lone pair over here. Let's evaluate these lone pairs. Let's start with this one here that I have in the green circle. You can see that there's no p orbital next door to the lone pair. Therefore, it's going to be localized. If you look at this carbon right here, that carbon is sp3 hybridized. Therefore, there's no empty p orbital or no p orbital at all there. So therefore, that lone pair is localized. If we go to this lone pair over here, I'll highlight it in yellow. You can see that you have a p orbital over here and you have a p orbital over here. How did you know that, Mr. Dion? Because this carbon is sp2 hybridized and this carbon is sp2 hybridized. But that nitrogen has a lone pair, but it doesn't have a pi bond. And so the lone pair can participate in resonance, therefore it's delocalized. The last one, last lone pair, which is this one, oops, oh crap. There we go, come on. The last lone pair, which is this one right here, is localized as well. It is next door to 2 atoms that have p orbitals. This is sp2 hybridized, this carbon, and this carbon is sp2 hybridized. However, the nitrogen has a pi bond on it. And since it's got a pi bond, the lone pair is not going to participate in resonance. So that lone pair on that nitrogen is localized. And there you have it. Those are the rules for recognizing whether lone pairs are localized or delocalized. Again, one of the rules, or the two rules that I think you really need to memorize here, is that the nitrogen in an amide, so I'm going to draw it here. If you have an amide, the nitrogen in an amide, even though it looks like it's sp3 hybridized, it's sp2. The reason why we know it's sp2 hybridized is because the electrons can participate in resonance. So I would memorize that. And the second thing I think it's wise to memorize is that when you have pyridine, and I'll redraw it up here, you have a pyridine molecule, which is this molecule here. You take an aromatic ring and you replace one of the carbons with a nitrogen. This lone pair is sp2 hybridized. It is not participating in resonance. Why? Because the nitrogen already has a pi bond on it, and the pi bond comes from the overlapping of these two p orbitals that are touching like that. And lastly, just because a lone pair, don't assume that a lone pair is delocalized just because it's next door to a pi bond, right? If we look at this lone pair, it's next door to a pi bond, but it's localized. Why? Because the nitrogen has a lone pair and a pi bond, and both cannot participate in resonance, so the lone pair is localized. Again, if you have a lone pair and it's next to an atom that has no p orbital, then it has to be localized. No ifs, ands, or buts.